Hi, my name is Nikki Swift. Welcome to my presentation titled The Physiological Response to Fear. This presentation is my assignment for Module 3 of the Dog Genius Level 5 Diploma in Equine Welfare, Training and Behaviour. The horse's body is made up from a variety of physiological systems that all interact with each other. Listed here are some of the systems we'll touch upon in this presentation that are involved in fear response. So we have the nervous system, the endocrine system, which is all about hormones, cardiovascular, respiratory, digestion, and musculoskeletal system. So we're going to start with the nervous system. This is divided into two parts: the central nervous system, which consists of the brain and the spinal cord, and the peripheral nervous system, which is all the other nerves in the body. Information travels via the nerves to and from the central nervous system. In terms of the fear response, afferent nerves are providing sensory information to the central nervous system, such as what we see, what we hear, what we feel. Efferent nerves are doing the opposite and carrying information away from the central nervous system to activate the involuntary autonomous nervous system and the voluntary somatic nervous system. We'll look at both of these in more detail later on, but first of all we need to look at the input to the central nervous system. So the sensory input to the central nervous system, it isn't just our external senses, sight, sound, smell, touch, taste, but it's also our internal state. And that includes things like our temperature, whether we're hungry, pain, illness, and our emotional state. So sensory integration is just that. It's the integration of all the senses, both internal and external. So what happens in the central nervous system when it receives this information? Well, first of all, it's received in a part of the brain called the thalamus. The thalamus then sends information to both the amygdala and the cortex. The route straight to the amygdala causes a reaction, which can be overruled by feedback from the cortex to the amygdala. So, for example, I have a real fear of snakes, and if I am out walking and out the corner of my eye I see a brown branch on the ground, instantly my heart rate goes up and I will startle. Then within seconds, my visual cortex recognises this as a branch and not a snake, feeds that information to the amygdala, and my initial response is overruled and I can start to calm down again. Information from the amygdala then travels to the hypothalamus. And the hypothalamus is responsible for maintaining homeostasis, which is the normal range for bodily functions, including things like temperature, heart rate, and stress. Any deviation from the normal range, and the hypothalamus activates processes within the body to rectify that. And that leads us nicely into the sympathetic and parasympathetic nervous systems. I mentioned earlier about the autonomic nervous system and said that responses via this system were involuntary. And if we look specifically at a fear response, once the sensory information has been identified as a threat, the autonomic nervous system kicks in very quickly. It's a very fast response because it has to be, because this is an evolutionary response to ensure survival. So this is my initial reaction, that the branch looked like a snake. And then through a series of events, the hypothalamus activates and releases adrenaline and noradrenaline from the adrenal gland. This then activates the sympathetic nervous system while deactivating the parasympathetic nervous system. The sympathetic system is all about responding to threat. You'll often hear it referred to as the fight or flight response, and the opposite response, the parasympathetic nervous system, is described as rest and digest. So these two systems are not mutually exclusive and they work with and balance each other. My initial response to the branch was via the sympathetic nervous system, with the parasympathetic nervous system kicking in very quickly once my brain realises there is no threat. So for the horse, an animal that has evolved to respond quickly to the threats, a stimulus such as a sound or a movement triggers the sympathetic nervous system. This changes the physiological response of the body to prepare for flight. It increases the heart rate and the breathing rate, meaning that more oxygenated blood is supplied quickly to the muscles. External senses become more acute. So for example, the pupils will dilate to increase vision. And resources are diverted from all of the non-essential bodily processes such as reproduction and digestion. And the opposite is true for the parasympathetic nervous system. So the sympathetic nervous system is the fast response to fear. The longer term response happens through hormones in the endocrine system. This is also triggered by the hypothalamus via the HPA axis, that's the hypothalamus pituitary adrenal axis. So eventually, through a cascade of responses, this results in the release of the hormone cortisol from the adrenal gland that sits just above the kidneys. This increases blood pressure, suppresses the immune system, and it releases additional energy required for flight. The HPA axis has its own feedback loop, and when the body has released enough cortisol, the hypothalamus will start to decrease the release of it. Unless, of course, the body is chronically stressed and the feedback loop dysregulates, but that is something for another presentation. And finally, how does the body actually take flight? Well, it sounds obvious, but by moving the legs and the muscles. This is a voluntary response via the somatic nervous system. So I mentioned earlier about efferent nerves transferring information from the central nervous system, and this is what happens here via motor neurons to muscles, which then allow the skeleton to move and the horse can take flight. It's also important to talk about things that affect the activation and the intensity of the flight response. So baseline arousal levels matter. The diagram on the right is called the window of tolerance, and it's a visual display of how arousal might affect the horse's response to stimuli. So when a horse is in the optimal arousal window, although the sympathetic nervous system might still activate when they recognise a trigger, the flight response might be less intense and more recoverable, with the parasympathetic nervous system coming back online very quickly. The top levels are described as hyper and hypoarousal. Hypoarousal is the highest, and in the horse, this may cause them to stop and stare in the direction of the trigger. Arousal might decrease slightly, but it's still high, and then the flight response activates in hyperarousal. And in these higher arousal states, the intensity is likely to be higher and the recovery takes longer. Or the horse might actually react to stimuli that they were okay with yesterday. And these levels of arousal, or the window of tolerance, can change size. So what influences the size of the window? Things like stress, pain, poor welfare, and trigger stacking can all influence both the size of the window and where the horse currently sits within that window. And these are all things that we should be considering when the horse has what we might describe an abnormal or an out of proportion response. So just to summarise, the flight response is a natural adaptive behaviour. The input to central nervous system is influenced by both external and internal sensory information. The nervous system influences the response of other physiological systems such as the cardiovascular, respiratory, digestive, and the musculoskeletal system. Sympathetic and parasympathetic nervous systems work alongside each other, and the flight response is modulated by learning and arousal. And that brings me to the end of the presentation. Thank you so much for listening. References are included in the last slide.